Welcome to Let's Read, The Case for a Creator by Lee Strobel. Today we're examining Chapter 7, The Evidence of Astronomy, the Privileged Planet. This chapter is Strobel's investigation into the fine-tuning argument from the characteristics of the Earth. Last chapter we looked at the argument from the apparent fine-tuning of the laws of physics, and here we're going to look into whether the Earth itself was designed precisely for intelligent life. The chapter opens with what Strobel wants to suggest is the standard atheist or scientific belief that life is common in the universe. He quotes Carl Sagan as suggesting there may be a million advanced civilizations in the Milky Way alone. However, he then goes on to falsely characterize why scientists believe this, saying, "After all, the forces of nature are so automatic that life is sure to have evolved wherever water exists. That's why, whenever scientists raise new speculation about liquid water being present on another celestial body, the underground worlds of Jupiter's frozen moons Europa and Ganymede are currently the most fashionable examples, then the automatic assumption is that living organisms must necessarily and inexorably follow." This is simply setting up a straw man. The basic argument that people make in support of the idea that life may be common in the universe is not based on the idea that water somehow inevitably leads to life. No sensible person believes that. And furthermore, few people even believe that water is absolutely essential for life. We currently have almost no idea about the necessary conditions for life, and so to simplify things, we have this extremely preliminary idea that we should look for life as we know it. Life, as we know it, is based on water, and water is something that we can look for on other worlds. Even if liquid water did not exist anywhere else in the universe, this would only rule out Earth-like life, not life in general. Since Strobel's not going to do a decent job of actually presenting the argument for many intelligent species, he's just going to dismiss it with that kind of straw man's. I'll present the argument for him. And the argument is simply this. 1. There are trillions of stars in the universe. 2. Even if only a tiny fraction had the necessary characteristics for life-supporting planets, that'd still be trillions of planets. 3. Even if the conditions for intelligent life arising are unlikely, that would still be millions of civilizations. So to argue against that, Strobel will need to establish that the fractions at each step are much smaller than, say, 1 in a trillion. Because there are trillions of trillions of stars in the universe, he needs to argue that the chances of any one of them producing a life-supporting planet is worse than 1 in a trillion. In the next section, Strobel introduces Frank Drake and his famous Drake equation. The Drake equation is a formula for calculating the number of advanced civilizations that exist in the galaxy, and Strobel characterizes it like this. Though the specific numbers that scientists then plugged into Drake's equation mostly amounted to rank conjecture fueled by their own biases, one scientist admitted that it was a way of compressing a large amount of ignorance into a small space. This did lend an air of scientific certainty to a highly speculative issue. Again, Strobel is setting up a straw man. The Drake equation was not meant to provide a simple answer to whether other advanced civilizations exist, or to provide some kind of veneer of rigor to plain bias. What it is a framework that sets out the unknown quantities that we would need in order to answer the question well. That is, if we actually want to know how many advanced civilizations there are in the universe, this gives us a good framework that says these are the quantities that you need to have a good idea about, and if once you have a good idea of all of them, then you will have some kind of answer. So go off and calculate these, find out what these numbers are, and as you do more research, you'll get better answers. And since it was proposed, research has continued, and some of the numbers in the equation that were just speculative at the time are now much better established. Now, we aren't anywhere near to having a good answer yet, but the Drake equation does give us a roadmap. And to suggest that it's simply an attempt by scientists to try and smuggle their biases in is simply wrong. Anyway, Strobel then asserts that science is now actually showing that the Earth is far from an average planet, and therefore the number of other civilizations is probably 0. This doesn't actually follow, since, as far as I can tell, the actual argument, as I know it, doesn't actually rest on Earth being average. We don't need to have an average Earth. It just needs to be no less common than 1 in a trillion. So even if the Earth is incredibly unlikely, it has to be only more likely than 1 in a trillion. That's the target that Strobel actually needs to aim for, and he's actually avoided that so far. In the next section, Strobel introduces the book Rare Earth by Peter Ward and Donald Brownlee, and to Strobel's credit, these authors are not religiously motivated intelligent design advocates, unlike many of the other authors that he's referenced. Also, his characterization of their book is actually quite fair. Ward and Brownlee argue in their book that the Earth is very rare, and possibly that no other planets in our galaxy have precisely the same set of characteristics. Look, this is generally agreeable, although many would actually argue over exactly how rare the Earth is. The second claim that they make is that the set of characteristics that make the Earth so rare is also the set of characteristics that is necessary for complex life to evolve. That is, not only is the Earth rare, but there is no other possible combination of characteristics that could allow life to exist. And that, of course, is a much more contentious claim. However, Strobel doesn't actually want to present any evidence or argument at this point. He just wants to quote the experts to give us the impression that intelligent design is intellectually respectable. I'll just note that this is the same tactic he uses every chapter, and move on to the next section. So here in the fourth section of the chapter, Strobel finally gives a basic statement of the argument for his chapter. Quote, Earth's location, its size, its composition, its structure, its atmosphere, its temperature, its internal dynamics, and its many intricate cycles that are essential to life, the carbon cycle, the oxygen cycle, the nitrogen cycle, the phosphorus cycle, the sulfur cycle, the calcium cycle, the sodium cycle, and so on, testify to the degree to which our planet is exquisitely and precariously balanced. Note, this argument is not even valid. Firstly, he would have to actually establish that the degree of balance is to a precision that is at least 1 in a trillion, as I've previously said. Any less fine-tuning than that, and you can't actually rule out chance as some kind of explanation. And secondly, he's equivocating on the term life. All of these factors are exquisitely balanced for life, as we know it. But for this argument to hold, he actually needs to establish that all of these conditions are also necessary for any kind of life. And that's a much harder proposition to support. Of course, Strobel isn't actually aware of the failings in his argument, so he proceeds to provide evidence for its claims, that there are many characteristics of the Earth that are unique. His main source in this section is the introductory geology textbook Earth by Frank Press and Raymond Seaver, and as far as I can tell, this seems to be a mainstream textbook. And even though it does list all the intricate geological systems of the Earth, it certainly doesn't conclude that therefore there must be an intelligent designer. To get to that conclusion, Strobel actually turns to a creationist and intelligent design advocate, Michael J. Denton, who isn't even actually qualified to discuss astronomy or geology. Anyway, so that's Strobel laying out, laying the groundwork, trying to soften us up with some straw men. Strobel now finally introduces the subject of his interview for this chapter, and in this chapter it's actually 2 people. And the reason that he's interviewing both is that they co-authored a book called The Privileged Planet, which this chapter, it seems to be, is just a rehashing of that. So Strobel does his usual thing of going through their biographies, describing them physically, none of which is particularly compelling. The 2 interesting parts of their biographies are that Richards has degrees in philosophy and theology, neither of which makes him qualified to actually discuss astronomy. Strobel's stated goal way back in chapter 1, I believe it was, or 2, was to interview experts. So I'm not quite sure why Richards is brought in for this, argument from astronomy. Anyway, the other interesting thing is that since this book was published in 2004, the other person he's interviewing, Gonzalez, has gone on to feature in quite a few controversies regarding his intelligent design advocacy. His promise as a sort of promising young astronomer, as it were, really seems to have petered out in the last 10 years or so, with him barely publishing or producing any kind of scientific research. Anyway, I only mention this because Strobel likes to include these biographical bits, and I'm not particularly a fan of the argument from authority, so I like to provide some balance. Next section. The interview starts with a discussion of the Copernican principle. Put simply, the Copernican principle, named after Nicholas Copernicus, is that Earth is not in some kind of special place within the cosmos. This was a direct repudiation of the religiously inspired geocentric views of the cosmos that had come before that had asserted that Earth was central to the universe, either physically at its centre or at very least centrally important to the purpose of the universe. Richard sums up the long-term impact that the Copernican principle has had as follows. Humans have been stripped of their false sense of uniqueness and importance. While religious folk continued to insist that there is something unique, special, intentional, and purposeful about our existence, scientists maintain that the material world is all there is, and that chance, an impersonal natural law, alone explains its existence. Richards is employing the familiar apologetics technique of strawmanning physicalism and methodological naturalism as some kind of dogmatic assumption of scientists rather than established by the successors of these approaches. The Copernican principle came about as part of an attempt to understand why the planets and stars moved the way they did across the sky. It was a rejection of the religious dogma that the Earth must be central to creation. And the whole Copernican principle was based only on the evidence of and reasoning from natural observations, and it was then borne out by further experimentation. It was not dogmatically held, and it will be rejected as soon as it's shown false, and not before that. Also, a pragmatic application of the Copernican principle is to simply recognise that if we do find ourselves in an unusual or special place within the cosmos, then this needs to be explained. But that first needs to be established, not asserted. Richards then argues that there never was a view that the Earth was at the centre of the universe, and that this is simply a myth. Unfortunately, he starts off quite poorly, referring to Galileo, Copernicus, and Kepler, as if they were misquoted as supporting a geocentric cosmology. I mean, this is stupid, as they were some of the key figures in arguing against geocentrism and for heliocentrism, or the model that the sun is at the centre of the solar system. Anyway, Richard spends 3.5 pages arguing that we've misunderstood the ancients' view of the cosmos, and that they didn't actually believe that the Earth was at the centre of it, but rather at the bottom of it. To me, the funniest part of this is when he tries to use Dante to show this. Their explanation of Dante's cosmological model is that God is at the top or on the outside, man is in some kind of intermediate part or in the middle, and hell goes down in 9 levels down to Satan's throne. To me, God, man, Satan really does seem to be putting people in the centre or in the middle, as it were. Anyway, the broader point is whether this is even relevant to what we're supposed to be arguing. Their argument in this section seems to be that scientists have dogmatically accepted the Copernican principle simply because it was a rejection of pre-scientific ideas, but that it isn't really a rejection of pre-scientific ideas, because people didn't actually believe that stuff, and therefore scientists shouldn't accept the Copernican principle. Richard says, it's very important, if you're going to advance the Copernican principle, that you make it look like it's grounded in the historical march of science. But when you actually look at the data, it's just not true. Of course, this is simply wrong. The Copernican principle is either true or not. We either do occupy some privileged position within the cosmos, or we don't. And that is true or not, regardless of what actually motivated its formulation. It is advanced by scientists not because of its position in history, but rather because it actually fits the data well. As far as we can tell, we are not the centre of the solar system. The solar system isn't, our sun, us are not the centre of the galaxy, and our galaxy is not the centre of the universe. Look, to further this non-argument, Richards and Gonzalez then draw an analogy to the flat Earth myth. Apparently, according to them, most educated people in Western cultures have known that the Earth is a spheroid for most of the last 2,000 years. Now, I'm not sure that most educated people knew it actually means that most people knew it. It's still quite possible that the uneducated masses still believe the world to be flat, but regardless of that, it's not even relevant. Even if no one ever believed in a flat Earth, it still wouldn't mean that no one believed in a geocentric cosmos. And even if that was true, I'm not quite sure whether people believed it or not is actually relevant to whether the Copernican principle is useful and true. Anyway, Gonzalez closes this section with a summary of their argument, saying, We found that our location in the universe, in our galaxy, in our solar system, as well as such things as the size and the rotation of the Earth, the mass of the Moon and the Sun, and so forth, a whole range of factors conspire together in an amazing way to make Earth a habitable planet. And even beyond that, we found that the very same conditions that allow for intelligent life on Earth also make it strangely well suited for viewing and analysing the universe. This is probably the best summary of the argument that is actually given in this chapter. The key parts of this claim is that these factors are necessary for a habitable planet, not just sufficient. That is, that there's no other way that life of any kind could exist, or that the only other ways are even more unlikely. I wait with anticipation to see if they can support this claim. The next section is Strobel setting up another straw man for Gonzalez and Richard to beat up. The straw man in this case is the idea that liquid water inevitably leads to life. We've seen this before, and I'm not going to bother covering again. Suffice to say that no one actually believes that. What is interesting is Gonzalez's take about what he believes is necessary for life. Quote, "It's true that in order to have life you need water, which is the universal solvent, for reactions to take place, as well as carbon, which serves as the core atom of the information-carrying structural molecules of life. But you also need a lot more." When Strobel points out that people have proposed non-carbon-based life, and Gonzalez responds by saying, that just won't work, and there's something like half a dozen different properties of both water and carbon that are optimal for life. The problem with this argument is that life as we know it evolved in a comparatively water and carbon-rich planet. It is hardly surprising that the chemical properties of these structures are intrinsic to life as we know it. What hasn't been shown is whether any kind of intelligent life is possible with other biochemistries. Even if water and carbon biochemistry is optimal for life, as Gonzalez asserts, that doesn't actually mean that it's the only way. This is essentially just an argument from ignorance. That there are no known alternative biochemistries means that it's reasonable, when looking for extraterrestrial life, to concentrate on water, but it certainly doesn't mean that there's no other possibilities. Strobel goes on to point out that not all life on Earth exists in the same chemical environment, citing life forms that don't need oxygen to survive. Gonzalez's response is, "The only things down there that don't need oxygen are some microorganisms that breathe methane, but larger organisms, which need to regulate metabolism, are invariably oxygen breathers." And that's it. That's the entirety of Gonzalez's argument for the necessity of oxygen to life. Simply that life on this planet seems to need oxygen to grow beyond a certain size. I mean, this is so full of holes that it's hard to know where to begin. Firstly, the argument is invalid. That all known large organisms require oxygen does not establish that all possible large organisms require oxygen. This is the hasty generalization fallacy, as we only have one planet with life to base this assertion on. Secondly, the Earth is comparatively oxygen-rich, and oxygen is highly reactive in a chemical sense. So, of course, life on Earth is adapted to take advantage of this fact. This hardly means that complex life will always require oxygen. Also, it's unlikely that complex life on Earth would actually evolve to not use oxygen, since it will likely be outcompeted by oxygen-using life. And that's it. That's Strobel's entire investigation of the biochemical necessities of life. Gonzalez and Richards have only narrowly beaten up Strobel's straw man, which kind of shows how tenuous that argument that life requires water, carbon, and oxygen really is. Note that this section is crucial to the argument for design. In order to conclude that the Earth is fine-tuned for life, it really is absolutely necessary to establish that life does, in fact, rely on the Earth being exactly the way it is. That they haven't actually managed to produce any actual evidence for this means that no matter how unlikely the Earth is, even if the Earth is terribly unlikely, it's quite possible that life could exist on planets that are completely unlike ours. And so at this point, their argument is shot. They've got nothing else, but they don't realise it, so we've got the rest of the chapter to go. In the next section, Strobel turns to consider how frequently stars have life-supporting planets. Strobel asks Gonzalez whether it's reasonable to assume that of the billions of stars in the Milky Way, at least some of them support life. His response is to argue that much of the Milky Way is actually unsuitable for life-supporting solar systems, and he illustrates this by talking about globular cluster M13, saying, "The problem is that if the probability of life at any one star is 0, then the probability for all stars remains 0. Gonzalez then goes on to claim that a globular cluster is one of the worst places in the entire galaxy to expect any life. Now, there are several problems here. My first objection is that his claim that the probability of life on any particular star in M13 is 0. Normally, it's not actually that important to distinguish between events that have an incredibly low probability and events with a probability that is actually 0. But in this case, it actually is important to draw that distinction. He is technically correct that if the probability for any given star is 0, or for each star is 0, then the overall probability is 0. It's just that the probability for any given star isn't 0. A probability of 0 literally means that something could not possibly be true. No one assigns a 0 probability to anything that isn't false by definition. Even Richard Dawkins doesn't assign a 0 probability to the existence of God, or fairies, or leprechauns. Reasonable people know that an actually 0 probability is almost always outside the bounds of empirical reasoning. Anyway, another problem with this argument is the subtle shift that he's done from discussing the Milky Way to discussing M13. Now, it is true that M13 is unlikely to have intelligent life within it. Now, the main reason, which Gonzalez has actually skipped over, is because it's actually quite small. There are approximately 300,000 stars in M13, which means that if the precise characteristics necessary for life are unlikely, then it probably is unlikely that there are any advanced civilizations in M13, but that doesn't actually apply to the Milky Way as a whole, which has not 300,000 stars, but hundreds of billions of stars. Gonzalez goes on then to explain why globular clusters like M13 are unlikely to have the right elements to support life. And this is actually a decent argument. Globular clusters usually consist of very old stars, and they have very low levels of heavier elements. Now, it might be possible for life to form from lighter elements, but our understanding of chemistry suggests that the kind of complex molecules that we think are necessary for any kind of life are simply not possible to form out of lighter elements, we think. Anyway, in an earlier section, Strobel introduced the Arecibo message, not that he called it that, which was a radio transmission that was made in 1974. The Arecibo radio telescope in Puerto Rico was remodeled, and as part of the ceremony to honour this, Frank Drake devised a message, with help from Carl Sagan and others, that could potentially communicate information about humanity to any extraterrestrials out there. In many ways, it was similar to the plaques that we put on the Pioneer spacecraft and the Golden Record on Voyager. And in many ways, it was really just a simple precursor to these ideas. Now, the reason that Strobel and Gonzalez have been talking about M13 is because that's where the Arecibo message was beamed to. Since Gonzalez concluded that M13 couldn't possibly have any life, he goes on to say, "It's really surprising that they would think there would be any chance of a civilization receiving their message in a globular cluster. Frankly, I think they were so deluded by their complete belief in the metaphysical Copernican principle that life was just going to be everywhere in a galaxy that they overlooked the facts." The problem with this is that it's simply wrong. And so wrong that I'm sure that Gonzalez is either dishonest or incompetent. The reason that the message was beamed to M13 is actually just because it was a convenient piece of sky to aim the telescope at for the ceremony. Furthermore, because M13 is 25,000 light years away, by the time the message gets that far, M13 will have actually moved and won't even actually receive the message. And this was known at the time. And the sending of the message was really just a demonstration of technical ability, a symbol of humankind reaching out to the stars. I mean, just like the Pioneer plaques and the Voyager gold records, no one seriously thought they had any real chance of being intercepted, interpreted, and responded to. I mean, this was much more of a cultural activity than a scientific one. Although, it did provide us with a good prompt to think about the difficulties of communicating with extraterrestrial life forms that have absolutely nothing in common with us. Although the previous section started off as if it was going to be some kind of investigation into the likelihood of finding life-supporting planets in our galaxy, it actually devolved into an attack on Drake and Sagan. So in this section, Strobel gets around to looking at what actually makes a galaxy hospitable for life-supporting planets. Gonzalez starts by talking about spiral galaxies, like the Milky Way, saying, "Our type of galaxy optimizes habitability because it provides safe zones, and Earth happens to be located in a safe zone, which is why life has been able to flourish here." Now, in the previous chapter, we discussed the weak anthropic principle, which essentially states that if intelligent life exists, it's hardly surprising that it will exist in places that are able to support intelligent life. What this means is that Earth doesn't just happen to be in a safe zone. As if it wasn't in a safe zone, intelligent life wouldn't have evolved on it, and we wouldn't be here to be having this discussion. That is, the question isn't, why did life evolve on a planet in a safe zone? But rather, a much better question is, how many planets are there in these safe zones? If there are many planets that could support life, then it's hardly surprising that we're here. If the safe zone is so restrictive that it's unlikely for life to have risen at all, then this actually would be supportive of Gonzalez's argument. Gonzalez goes on to explain how there is essentially a restricted section of a galaxy like the Milky Way that is conducive to planets like ours forming and surviving. That is, his contention is that life-supporting planets can only really exist in a narrow band in the galaxy. Now, the problem with this is, even if he is 100% correct, his estimate is that approximately 1 in 20 stars in the Milky Way are in the safe zone. Now, while 1 in 20, or 5%, may sound like a small number, remember that the galaxy has hundreds of billions of stars, leaving, on his 5% estimate, billions of stars that are actually in the safe zone, according to him. However, that's not actually the conclusion that Strobel wants his readers to come to, so he omits the actual numbers, so he can still say that the Earth is pretty special. In the next section, Gonzalez explains why galaxies that aren't spiral galaxies are unsuitable to life. Now, while I think he's really overreaching beyond what the evidence actually shows, it's not even a strong point, because spiral galaxies make up about 20% of all galaxies, and barred spirals, like the Milky Way, are about 2/3 of these. That is, the Milky Way, our galaxy that supports intelligent life, is representative of about 13% of all galaxies. So given that there are hundreds of billions of galaxies, that means there are still billions of galaxies like ours. And each one has hundreds of billions of stars in their habitable zone, according to Gonzalez's own figures. So that gives about 100 trillion stars in the universe that are in the right zone for life in the right kind of galaxies. So to head off this uncomfortable conclusion, Richards chimes in to shift the topic back to the Copernican principle, saying, "Very often, the Copernican principle describes properties that don't matter. Who really cares whether we're in the physical center of the galaxy? It's irrelevant. What really matters is being in the place that's most conducive to life. And that's exactly where Earth finds itself." Actually, being at the center of the universe was pretty much a core tenet of many religions until it was shown to be wrong. It's a reasonable prediction from the God hypothesis. And it's actually a good example of how any actually falsifiable prediction made by religions have turned out to be false. And also, to find ourselves in a place that is conducive to life is not an argument for intelligent design. It's exactly what we'd expect if there had been no design. Now Gonzalez goes on to discuss extrasolar planets, that is, planets orbiting other stars. At the time of printing of this book, which was 2004, The only planets that we'd been able to observe, even indirectly, were Jupiter-sized gas giants, and many of those were what were called hot Jupiters, since they orbit their stars at extremely close range, very much not like our solar system. From this, Gonzalez argues that this means that solar system arrangements like ours must be unlikely, and with the benefit of another 10 years of astronomy, we actually know that to be false. But even 10 years ago, this was an obviously wrong and false argument. I mean, the first extrasolar planets that we were able to observe were always going to be the biggest. I mean, our detection methods involve detecting, so we look at a star, and every now and again the brightness of that star seems to dim, and dim, and based on that and a whole range of sort of much more technical stuff, essentially, we can infer that it's dimming because there is a planet passing in front of it. That is, there's a planet orbiting it, passing in front of it. So, the most easily detected of these kinds of systems will be large planets orbiting bright stars with high orbital frequencies. These are the kinds of planets that are much more detectable because they produce the strongest signals. Bright stars, so we can see them better. Large planets, so there's a much more noticeable dip in thing. Close to the star, so that there's a nice high frequency of flashing. Because if it was only happening once every 400 years, we wouldn't be able to observe the 400-year blip in front of it. These are the kind of planets that are much more detectable, and that's what we found. Since what we found is in line with what we expected to find, it's not actually an argument that these kind of planets are somehow more likely. Anyway, next section, Gonzalez goes on to argue that a Jupiter-sized planet in a stable circular orbit in the outer solar system is essential to the formation of life in a solar system. His argument is such a large planet further out in the solar system helps to deflect incoming comets and other celestial bodies that would otherwise bombard a planet like ours and destroy any burgeoning life forms. He then goes on to detail how the actual details of our solar system, that is the position, the placement of other planets, their orbits, etc., all contribute to the Earth being the way it is. And the problem with this is it doesn't actually establish that any of these factors are actually necessary for life to arise, just that they're necessary in our particular case. I mean, it does nothing to show that there aren't different solar system arrangements that could also produce life-supporting planets. Next, we get a brief tour of the circumstellar habitable zone, or more colloquially known as the Goldilocks zone. This is the area around a star where the temperature is just right to allow for liquid water to exist on a planet. Any given star has a range of orbital distances, which kind of also depend on the atmosphere of the planet and any other heating effects, but any given star will have a habitable zone or Goldilocks zone. So Gonzalez claims that even a 5% variation in the Earth's orbit would take us out of this zone, and this is simply incorrect. The Earth's orbit isn't circular, it's elliptical. And the variation in our distance from the Sun is roughly 3%. So just in the course of a year, we have a 3% variation in our orbit, and that's perfectly fine. But also, estimates of the size of the habitable zone in our solar system kind of depend on whether you allow for changes in atmosphere and stuff. So if you just shift the Earth, but even the most conservative estimates for it allow for a 6% variation. The most conservative estimate I could find said that we could move from 0.95 of our orbit to 1.01 of our orbit, which would be a 6% variation, give or take. Actually, a bit more than that. But that's okay, because we don't talk numbers in this book, apparently. Next section, Gonzalez argues that a life-supporting planet requires a particular kind of star. And that kind of star is one like our Sun. He details over 3.5 pages all the ways in which our Sun is highly unusual, in precisely the way that is needed to allow life. The problem with this is that stars like our Sun may not be particularly common, but they're hardly as rare as Gonzalez wants to make out. Estimates for how common they are vary, but many seem to agree that it's in the low single-digit percentages. And probably a representative number of what the estimate would be, about 5% of stars near our solar system are like our sun. And this is significant because even if sun-like stars were vanishingly uncommon in the rest of the galaxy, we're only really interested in that small sliver of spiral galaxies that Gonzalez has referred to as the safe zone. And if our local region is typical of such safe zones, and honestly we have no evidence that it isn't, then it's quite possible that about 5% of stars in the safe zones are like our sun. So a few sections back I calculated that by Gonzalez's logic there are about 100 trillion stars in the universe in the safe zone of a barred spiral galaxy. So from this we can conclude that about 5% of those, or 1 trillion stars, would be sun-like. So it'd be in the right galaxies, in the right places within those galaxies, and like our sun, and conducive to life. That's 1 trillion of them. Of course, Strobel doesn't actually want you to come to this conclusion, so instead he says, it would take a star with the highly unusual properties of our sun, the right mass, the right light, the right composition, the right distance, the right orbit, the right galaxy, the right location, to nurture living organisms on a circling planet. That makes our sun and our planet rare indeed. Now, to be fair, we do also need to restrict ourselves to stars that have the right orbital characteristics within their galaxy, and unfortunately I could find absolutely no estimates for that, for how many sun-like stars will actually have orbits like our sun. I'll leave that aside for now and I'll return to it later, but I just want to note at the moment that Gonzalez makes no attempt to even address that concern or even provide any numbers or estimates. In this section, next section, Gonzalez takes a couple of pages to explain how essential the moon is to the Earth being life-supporting. Again, the problem here is that he doesn't actually establish whether having a moon is rare or unlikely. The currently favoured hypothesis is that our moon was created by a collision between the Earth and a Mars-sized object. Now, one of the reasons that this collision hypothesis is favoured is actually because our planetary formation models in the early universe kind of predict that Earth would probably have had about a dozen such impacts, and it would only have needed one to produce the moon, which kind of suggests that it's not all that unlikely that our Earth would have ended up with a moon like that. Of course, Gonzalez isn't actually interested in how likely it is that such a moon would form through impact. Rather, he's much more interested in pointing out how precisely its effects seem to help with the Earth supporting life. Strobel finishes this section by quoting from James Casting, who is probably the world expert in planetary habitability. The moon is now generally believed to have formed as a consequence of a glancing collision with a Mars-sized body during the later stages of the Earth's formation. If such moon-forming collisions are rare, habitable planets might be equally rare. That if makes a difference. There are models that suggest that these aren't rare collisions, but Strobel's not interested in those. Next, Gonzalez argues against life existing in a water world, that is, a world without any dry land. His basic argument, which he's been using repeatedly in this chapter, is that life, as we know it, relies on Earth being the way it is. It really is that simplistic. And he finishes this section by saying, I don't believe it would be habitable. There would be no way to regulate the salt, so I certainly don't imagine there are any dolphins swimming around in there. It really is that bad an argument. Now Gonzalez argues against life existing on a world without plate tectonics, again using the same argument. Life on Earth depends on plate tectonics, therefore all life depends on plate tectonics. Also, as in every other section, he makes no attempt to quantify how unlikely it is for an Earth-like planet to have plate tectonics. He simply observes that we rely on the Earth's plate tectonics to be exactly the way it is in order to support the exact kinds of life that it does. And then he fallaciously concludes that it must be unlikely. This is the final section in which Gonzalez is arguing that our planet is fine-tuned for life. Strobel feels like he's made his case. Last time I did a count, we were down to about 1 trillion stars that were just like ours in the right section of the universe, the galaxy, etc., etc. We still need to estimate the proportion of those that would have the right galactic orbits, would have a moon, dry land, and plate tectonics. Of according to Gonzalez's arguments. These are all speculative questions. It seems to me that a moon isn't that unlikely, given our knowledge about planet formation. And it also seems to me that the existence of dry land and plate tectonics are probably to a degree not independent. That is, if you've got plate tectonics, that probably encourages dry land or vice versa. Look, I'm comfortable saying that the odds of a star like ours forming planets like our solar system would probably be in the range of, 1 in 100 to 1 in 1,000. Of course, this is based on nothing but speculation, guesswork, a reading of various articles, most of which came via Wikipedia. But still, my estimate, this is about, maybe 1 in 1,000, is more than Strobel's given us in this entire chapter, and certainly more than Gonzalez has given us. And at the odds of 1,000 to 1, which I'm kind of comfortable with, even 1,000,000 to 1, at the odds of 1,000 to 1, there would be 1 billion planets just like ours. Planets. 1 billion planets with all of these characteristics that Gonzalez has been saying is incredibly unlikely. There would be 1 billion of those in the known universe. That's hardly as unlikely as Strobel would have us want it to be. Anyway, that's it with showing that the Earth is fine-tuned for life. That's the best they've got, apparently. The next 4 sections, Gonzalez and Richards are arguing that our planet is not just fine-tuned for life, but also for science. That is, that the Earth is uniquely placed to allow us to discover the cosmos around us and to explore the universe. This starts with the coincidence of the apparent sizes of the Moon and the Sun that allow for solar eclipses to occur. Gonzalez says, "There's a striking convergence of rare properties that allow people on Earth to witness perfect solar eclipses. There's no law of physics that would necessitate this. In fact, of the 9 planets with their more than 63 moons in our solar system, the Earth's surface is the best place for observers can witness a total solar eclipse, and that's only possible for the near-term future." Although I agree with him here, Gonzalez is actually contradicting himself with this. So the fact that perfect solar eclipses, that is where the moon perfectly eclipses the sun, can actually occur on Earth, are a direct result of the sizes of the moon, the size of the sun, the orbital distance of the moon from the Earth, and the Earth's orbital distance from the sun. Now, the problem is that Gonzalez has already claimed that all of these quantities are fine-tuned for life on Earth, which means that they couldn't have been otherwise on his account. I mean, if all of these quantities must be the way they are in order for life to even exist, then it couldn't have been otherwise, regardless of whether they were designed that way. Anyway, the claim being made here is that solar eclipses allowed humans to learn about the cosmos, since we could measure the sun's spectrum during the eclipses, and we also used eclipses to confirm gravitational lensing, and hence to confirm relativity. He also claims that since eclipses were significant to ancient cultures, they were recorded in the histories of these cultures, and that's allowed us to look back, and because we can predict eclipses, this allows us to measure changes in the Earth's rotation. I'd just like to point out that you don't need absolute perfect eclipses for that to happen. Even imperfect eclipses would still be notable to ancient civilizations. The fact that Gonzalez doesn't pick up on this is a little bit of a bad sign about, how closely he's analysing his own arguments. But anyway, before addressing the other claims that they're good for learning about stars and for proving relativity, I want to look at the next section. So, next, Gonzalez wants to argue that our position within the Milky Way is perfect for astronomy, saying, "Our location away from the galaxy's centre and in the flat plane of the disk provides us with a particularly privileged vantage point for observing both nearby and distant stars." Now, I'm no astronomer, but I would have thought that actually some elevation out of the disk of the galaxy would actually be better for this purpose. Part of the problem that we have in estimating things like the size of our galaxy is that much of the galaxy is obscured by nearby stars within that galaxy because we happen to be within the disk of the galaxy. I would have thought that a slight elevation out of the disk would fix this, but I'm sure Gonzalez has some kind of excuse about why it's better to have our view blocked. Richards then goes on to cite the existence of deep snow deposits in the polar regions as another example of how our planet is fine-tuned for us to do science. His argument is that since the polar regions have continuously frozen ice layers, we can take ice cores and that documents the past, and we can then research that and learn from it. He then goes on to argue that our atmosphere is clear and therefore was designed for astronomy. His words, not mine. Strobel objects that surely our drive to put telescopes in space kind of shows that the Earth's atmosphere isn't that great for astronomy. Gonzalez's reply is, we're not saying that every condition of measurability is uniquely and individually optimized on Earth. This is the same old intelligent design dodge, that although their designer is the Christian God, it's not like he's all-powerful or something. I mean, he's constrained. He's got to compromise. You know, like in Genesis, God looked down upon the world and saw that it was good enough. Anyway, the next claim that Richard makes is that earthquakes are God's way of allowing us to do seismology. Seriously. Quote, one byproduct of the movement of these crustal plates is earthquakes, which in turn have provided scientists with research data that would otherwise be difficult to obtain. They've also provided thousands of people with death, injury, and untold suffering. But I'm glad that the intelligent designer thought that that was outweighed by our desire to get geological data that might have been difficult to obtain. The next section is called the trilemma of life. And I always like when apologists use the term trilemma, but since they're halfway to identifying their own fallacies for me. The trilemma that Gonzalez and Richards present is the same old intelligent design, false trichotomy. Our existence is either the result of random chance, physical necessity, or creation. The problem here is that these three aren't the only options. They may be the only options that we can come up with, but they don't actually exhaust all possibilities. Also, all through this chapter, Gonzalez and Richards have failed to mount any real challenge to the idea that the Earth came about through random chance. I mean, to discount chance as an explanation, you'd have to at least make some attempt to discuss probabilities. And on the rare occasion they have done, the probabilities that they come up with are laughably high, not low. They're in the 5% or 10% range, which is not low enough to discount chance. Anyway, after this brief interlude discussing intelligent design, we go back to looking at examples of the Earth being fine-tuned for life. Sort of. The next example given is that of pollen. So apparently Darwin argued that pollen and pollination couldn't have been designed at all because plants spreading pollen was this terribly inefficient process. Richards responds that because pollen contains carbon-14, we can use pollen trapped in ice cores and sediments to date those layers. That is apparently that the intelligent designer made plants so inefficient and wasteful with their pollen because he knew that we'd come along and want to do science with the absolutely tiny percentage of pollen that happened to get trapped in ice. Really? Before moving on to the last section, I want to finally address the examples that they've been bringing up to try and show that the Earth is fine-tuned for science. Examples like the fact that we have eclipses here. And the problem with all of these examples is that they're simply invoking the sharpshooter fallacy. That is, they're looking at the various disparate aspects of the Earth that support doing science and ignoring all the parts that aren't supportive of doing science. I mean, there are countless examples of the way in which the Earth is in a poor position for us to learn about the cosmos. I mean, there are large parts of the galaxy that we can't directly observe, and the atmosphere causes problems for astronomy, not helping it. And that's just to give the two examples that they've already brought up. I mean, given a random planet like ours, we would expect that in some ways it would be well situated for observing the universe around it, and in other ways it would be poorly situated. And that's precisely what we find when we don't cherry pick our evidence. The final section, thank goodness, is Strobel returning to consider intelligent design. He quotes from John O'Keefe, who is a Catholic and an astronomer, on the possibility of other life existing within our universe. He would have no theological problem if, indeed, other civilizations existed. That's the position of many Christians. God certainly could have created other life-populated planets that the Bible doesn't reveal. It's this kind of unfalsifiability that makes intelligent design such a non-explanation. If the existence of only one kind of intelligent life is evidence for intelligent design, as has been argued all the way through this chapter, and the existence of many kinds of intelligent life is also evidence for intelligent design, then what would actually count as evidence against it? I mean, if your God has nothing to say on whether we are or are not his sole intelligent creation, then he is hardly an explanation for our existence. The chapter ends with this summary from Strobel. If God so precisely and carefully and lovingly and amazingly constructed a mind-boggling habitat for his creatures, then it would be natural for him to want them to explore it, to measure it, to investigate it, to appreciate it, to be inspired by it, and ultimately, and most importantly, to find him through it. Yes, but not for us to actually go to his creation. I mean, apparently this God wants us to be confined to some vanishingly tiny fraction of the universe, despite it having been created entirely, not just with us in mind, but apparently for us to actually be able to explore it. I mean, at least the Garden of Eden didn't have Adam and Eve locked in the corner, unable to actually access the majority of it. I mean, this is the kind of theology that he is implicitly endorsing in his book. The good news is that's it for this chapter. The evidence for the fine-tuning of the Earth is, to put it mildly, underwhelming. Based on the arguments put forth, I get about 1 billion planets, just like Earth, in the rest of the known universe. I mean, that's hardly fine-tuned. Also, the only argument against life existing under radically different conditions was that 1, we don't know how that would work, and 2, that's not how it is here. That is, argument from ignorance and hasty generalization. Then we had the sharpshooter fallacy, to argue that the Earth is being fine-tuned for science, and false trichotomy fallacy of intelligent design. Again, I'm not impressed by the quality of argumentation or the evidence presented, but don't worry, there's still 4 more chapters to go, starting with chapter 8. The evidence of biochemistry, the complexity of molecular machines, which stars our expert from chapter 4, Stephen Meyer. Thanks for watching. See you next time.